All right. We're going to go ahead and get started. The Argos and Colby should be here soon, but let me pray for us, and then we'll talk a little bit about the structure of the class over the next several weeks until our semester ends, and then we'll get into Lesson 7. So let's pray. Father, thank you again for the opportunity that I have to come before you in prayer, and through that process become humbled and encouraged, knowing that, one, humbled because I know I can't handle everything on my own, and encouraged because I know that you're moved by our prayers, and that you promise to answer them. And Father, I just ask that this afternoon you would be with me and you would help me to think and to speak clearly. That you'd be with these students and you would help them to think and to speak clearly as well. And Father, as we work through this, I pray that you would give us a greater appreciation for how structured and organized your creation is, and a greater appreciation for what we're capable of doing within your creation as we model and think through things. And Father, I ask these things in the name of Jesus. Amen. All right, so this week we're talking about Lesson 7. Next week we won't meet, and the week after that we'll do Lesson 8, and the week after that we'll do Lesson 9, and that'll be the first week of December when we do Lesson 9. And then the last time we'll meet this semester is the following week. I think the week starts on the 11th of December, somewhere around then, and that's when we'll do Lab 4. And so if you need a grade for your semester, you just need to make sure that on that day where we meet to do Lab 4, you bring in everything that we've been working on up to that point. So the homework for Lesson 7, 8, and 9, Lab 3, which we did last week, and Quiz 3 and Homework 4, which we'll have when we come back from Thanksgiving. If you don't need a final grade this semester and you can wait until January, you can hold on to your stuff to turn in until January, and that'll be fine. So today, you owe me Homework 4, Homework 5, Homework 6, Quiz 2, Exam 2, and Lab 2. So if you have your folder, if you could tuck your homework and your lab in the pocket on the left, and your quiz and your exam in the pocket on the right, that would be really helpful. If you don't have your folder, that's fine. Just stack everything together, and I'll put your work in a new folder, and then you can have 2 folders. So, and everybody wins. I get to get rid of all these folders that are clogging up my desk, and you get 2 of them. So, all right. Any questions about the schedule for the rest of the semester? I'm sorry if you're upset that we aren't going to have class next week, but it's the Wednesday before Thanksgiving, so a lot of preparations being made. We're doing I know this means maybe very little to you, but each person is going to get our own individual Cornish game hen done like a Thanksgiving turkey. And for me, it's kind of cool. With the kids, it's going to blow their mind because they're going to have a tiny turkey just to themselves. Oh, they're going to love it. All right. So last week we did Lab 3. The week before that, we talked about kinetic energy. And kinetic energy is energy in any object that is in motion. And so this week we're talking about potential energy, and the first framing question we're going to discuss is this one. If the velocity of an object is 0, can it still have energy? If the velocity of an object is 0, can it still have energy? And simply put, the answer to this is yes, but it's not going to be kinetic energy, right? So if we tried to calculate the kinetic energy of this object, our formula for kinetic energy is 1/2 mv squared. And if the velocity is 0, right, we put 0 in there. It doesn't really matter what the units are at that point. So if we put 0 in there, what's 0 squared? What's 0 times 0? 0. 0 times whatever is 0. So the kinetic energy of this object that is not moving, the kinetic energy of an object with a velocity of 0 is 0. So it has no kinetic energy. However, the object still or can still have energy associated with its position. So not associated with its velocity, but associated with its position. And here's the basic idea for that. If we basically think about it this way. If the object has the potential to move, then it has potential energy. So if the object has the potential to move, it has potential energy. And this isn't like potential to move like, I was going to make fun of teenage boys, but I should refrain since most of the people in here are teenage boys. It's not like the potential to move like a dog, right, sitting on the floor that sure has the potential to stand up and walk, right? We're talking about the potential to move like something suspended, off the ground, or something at the top of a cliff that has a potential to basically be pulled down because of gravity. And so that's what we're meaning here when we're talking about the potential to move. And this is how we calculate it. So PE, potential energy, is equal to M times G times H. M is mass, G, acceleration due to gravity, and then H is the height. So again, potential energy, it's energy associated with the object's position and not associated with the object's velocity. M is mass, G is acceleration due to gravity, H is height. Now, what is acceleration due to gravity on Earth? Yeah? 9.80 meters per second squared. And so the nice thing is unless your problem specifically states that this object is not on Earth, G is always going to be the same, right? Mass will change depending on whatever the object is. Its height will change based on however high it's suspended off of whatever your zero height is, but G is always going to be the same. So in order to do this, we have to set some point to be height is equal to 0. And usually in terms of the problems that I'll give you, and most of the problems you're going to interact with, it'll say that you have an object suspended off the ground, right? And it'll make it very obvious that the ground is your height is equal to 0. And then so whatever that height is off the ground is going to be your height for this formula. I will do my best to try to make these questions as straightforward as possible. The sample questions I put in, and the homework problems that I wrote up, it's very clear. It says height above the ground, setting the ground as being your height equals 0. Now, if you want to make a different point, your height is equal to 0, you can do that, but just be careful when you do that. As we get into some other problems and we start talking about momentum transfer, sometimes it's beneficial to do that. But take what the problem gives you if it keeps it relatively simple. Did you have a question, Josh? Okay. All right. So again, potential energy, energy associated with position and not energy associated with velocity. So here's our first example problem. How much potential energy is in a 5.65 kilogram rock suspended 7.5 meters above the ground? So what is our 0, our height equals 0 point? Ground. The ground, right? Allow the problem what it gives you to keep things simple. All right, so what do we have, or what are we given by this problem? What does it give us?
Mass equals 5.65 kilograms.
Mass equals 5.65 kilograms. What else?
Height equals 7.5 meters.
Height equals 7.5 meters. Oh gosh, put my line in the wrong spot. 7.5 meters. And that's it, right? That's all we're given by the problem. We have a tool that we just introduced that links mass and height. What is that tool? Potential energy is equal to mass times the acceleration due to gravity times height. So another tool we have is we know what g is, because unless the problem specifically told us we weren't on Earth, we know what acceleration due to gravity is. Right? 9.80 meters per second squared. And then what is this problem asking us for? What do we want?
Potential energy.
Potential energy. The nice thing is our tool is already set up in such a way to calculate potential energy. So our potential energy is equal to the mass of the rock, which is what? 5.65 kilograms, times acceleration due to gravity, which is 9.80 meters per second squared, times our height, which is 7.5 meters. And so our units are going to be kilograms, meters squared per second squared. Right? If we multiply all those meters, have we seen these units before? What is a kilogram meter squared per second squared? It's a joule. So our units will also be in joules. Let's multiply these together. Hey, stop. So 5.65 times 9.80 times 7.5. How many significant figures is here? Or are here? Sorry, that was grammatically incorrect. How many significant figures are here? 3? How many here? How many here?
2.
So how many significant figures should our answer have?
2.
2. So we have 410 kilograms meters squared per second squared, or 410 joules. How do you want to represent those units? Everyone else get that when they calculated it out? Okay. So 2 significant figures gives us 410 joules, which isn't a huge amount of energy, but this rock also isn't very far off the ground, and it's not that massive of a rock. About 13 pounds or so, and 7.5 meters, 25 feet or so. So there is some energy there, right? But again, it's not energy associated with velocity, it's energy associated with what? With its position. Okay, so yeah, it's potential energy with its potential to move, right? Its potential to have velocity. So next one, how much potential energy does a 135.5 kilogram person about to jump out of a plane 750.0 meters above the ground have? It was a long sentence. So what do we have? What does the problem give us?
Mass.
Gives us mass and height again, right? What's the mass of this person? 135.5 kilograms. I use this person a lot because this is a big person. It's a big person. And I like big people. All right. Also gives us height. Height is 750.0 meters. I didn't say that to imply that I don't like little people. Just big people have, a special place in my heart. All right. Tools, we're going to use the same tool we used last time. Gave us the same values, right? It gave us the same, not values, the same tools or the same units, the same measurements. And so we have potential energy is equal to mass times acceleration due to gravity times height. We also know, because it didn't tell us that this wasn't happening on Earth, that g is equal to 9.80 meters per second squared. Right? What do we want? We want potential energy again, which is just wonderful, because our tool is already set up for us to find potential energy. But if you were given potential energy and it was asking you for something else, you could do that, right? We would just manipulate this algebraically to solve it for something else. And I should have had a problem do that. I didn't, nor in the homework, but that's okay. We'll have opportunity in a couple of weeks to do that. So we know the mass. The mass is 135.5 kilograms. We know G because we're on Earth, or at least it doesn't tell us otherwise. And we know the height, 750.0 meters. And so these units are going to, again, be kilograms, meters squared, per second squared, which is also equal to what? Joules. This has how many significant figures? 4. The middle one? 3. And the last one? 4. So our answer should have how many? 3. Same number as our fewest. So we have 996,000 kilograms meters squared per second squared. Or 996,000 joules. A lot more than our rock. But it's also 10 times the height of the rock and way more massive. That's a lot of energy. The only thing we had that came close to that is when we were doing the amount of chemical energy in a candy bar. Right? You're like, man, if you could harness all of that potential energy from that person jumping out of an airplane and then eat it, it would give you, about 1/8 of the number of calories you needed in a day. All right? Any questions about these? So this is potential energy. Energy based on position and not based on the velocity. So next framing question we're going to deal with is this. Does all of the potential energy convert to kinetic energy? So remember, we talked about potential energy as the potential to move. Right? And the energy in a moving object is kinetic energy. So does all of the potential energy convert to kinetic energy? What do you think? Yeah, I mean, in reality, the answer is no, right? So the simple answer is no. Like, it doesn't convert all from potential energy to kinetic energy. However, in order to keep our model simple, we say yes. So even though in reality it doesn't, because there's going to be other things involved, right? There's going to be friction. There's going to be all sorts of other things involved. So the simple answer is no, but to keep our model simple, we have to say yes. Because otherwise we have to know a lot of other information. So if y'all want to get into mechanical or civil engineering, then your answer will be no. And you'll figure out friction and all that has to do with it. My brother, have I told you that my brother's an engineer? My brother's an engineer. He's a structural engineer. He designs buildings so that they don't collapse under earthquakes. I don't know what that means for you. That's what he does. All right. So, potential energy will equal 0 whenever height is 0, right? So potential energy is energy associated with position. So if the position is 0, that energy is going to be 0. Just like kinetic energy is energy associated with moving, and so if it's not moving, it has 0 kinetic energy. And so at this point, all of the potential energy has been converted into kinetic energy. At least that's what we have to assume to keep our model simple. So at that point, whatever potential energy we had is now equal to the kinetic energy we have. So whatever potential energy we had is now equal to the amount of kinetic energy that we have. Which means we can take this problem here, our 135 kilogram person that's about to jump out of an airplane, and we can say, okay, well, if all that potential energy converts to kinetic energy, what's the velocity of that person when height is equal to 0, when they hit the ground? And hopefully, for their sake, they had a parachute, right, and increased friction on the way down, but we can do that. And this gives us a second way to do a free fall problem. So before, the only thing we could do with a free fall problem was to figure out how much time it would take to hit the ground from wherever it dropped from, right? And then you can go back using that time to try to calculate the velocity, but it'd be much more difficult algebraically. This is a lot simpler algebraically to do it this way. Okay? So, if we have a problem where the potential energy we had is equal to now the kinetic energy that we have, what's our formula for potential energy? Mass times acceleration due to gravity times height, right, is equal to 1/2 mass times velocity squared. Right, so if you're in a situation where all of your potential energy gets converted into kinetic energy, we can set up our problem like this. Let's clean this up a little bit. What if we decided we wanted to do this? Divide mass away from both sides. If you multiply mass and then you divide it away, you've essentially done nothing, right? So we can cancel this out, and we could cancel this out, and we could clean this up a little bit and say that acceleration due to gravity times the height is equal to 1/2 v squared. And if we want to clean this up a little bit more, because you don't like fractions. Do you like fractions? I like fractions. Most people don't like fractions. Fractions are fun because I think it's because it's controlled chaos, right? It's like not so easy to just look at it and know exactly what's going on. You have to think about it a little bit, but it's controlled. And controlled chaos is good. Way better than uncontrollable chaos. All right, so here we can clean this up a little bit. And if we don't want 1/2, we can multiply both sides by 2. Because 1/2 times 2 is what? If you have 2 halves, you have a whole, right? So this together would equal 1. And so now we have v squared is equal to 2 times g times h. I should have put all this in the slide. I don't know why I didn't. I will add it to the slide before I send you these slides out. I should have actually walked through this instead of waiting to our example problems to do it. And so now we can very quickly move from the height of an object to the velocity of that object if all the potential energy converted into velocity, or all of the potential energy converted into kinetic energy. But then we have one more question we have to deal with, and we'll have one problem where this isn't the case and another problem with this being the case. So what about if the height doesn't drop all the way to 0? So if it drops all the way to 0, obviously potential energy is going to equal kinetic energy, right? But what if it doesn't drop all the way to 0? Do you still have some energy associated with its position? You do, right? If it doesn't drop all the way to 0, you still have some potential energy. Does that make sense? So in that scenario, what you'd have to do is we have to calculate the new potential energy based on its new position. We have to subtract that away from the original potential energy, and then the difference is your kinetic energy. So we'll do a problem where all of our potential energy converts into kinetic, and then we'll do a problem where we still have some potential energy. We haven't lost it all. And you'll love it. Because then in 2 weeks, when we come back after Thanksgiving, we can do some problems where we're talking about momentum, and we're converting from kinetic to potential, back to kinetic, back to potential, like on a roller coaster, you know, where at some point it's at its maximum height, drops to convert it into kinetic, and then raises back up a little bit. We'll have some fun problems. Any questions here?
I have one.
Yeah.
Can we just calculate the potential energy and for H, just put the difference in H? Since the formula is
You
linear,
could.
but you just put the change in for H. You went from 75 meters to 50.
Sure.
And then just, if you use that in the formula, the difference between the two heights, it should
Yeah, because then that is taking the difference and just putting it into a single formula. Sure. Yeah, you could do that. Just put the change in H in there. If you're going to do that, you just need to make sure that you put your original height first, and otherwise you'll get a negative, which is fine because negative energies are fine. You just have to change the value over. Sure. All right. So what is the velocity of the 5.65 kilogram rock when it hits the ground? Oh, still dead. All right. So we still have what we had before. The mass is equal to 5.65 kilograms. Our height is equal to 7.5 meters. We still have this tool that says potential energy is equal to mass times acceleration due to gravity times the height. We still have that G is equal to 9.80 meters per second squared. And now we have an additional tool, this one that we just derived, where GH is equal to, 2 times G times H is equal to V squared. Right? Okay. And so what do we want? We want V. So we want V. So we have a tool right here that we can change a little bit algebraically to get V. Right now V is squared here. How do we deal with that? Yeah, we'll take the square root. And if we take the square root of this side, we have to take the square root of this side as well. So this tool could also be written as V is equal to the square root of 2 times G times H. Notice we don't have to worry about mass because the mass was in both of our equations. Why does that make sense that we don't have to worry about the mass when we're going from the height of an object to velocity? Thank you. Why does that make sense if we don't have to worry about the mass when we're going from the height of an object to a velocity? When we were doing free fall problems, did we worry about mass? We didn't, right? Because no matter what the mass of an object is, it accelerates due to gravity in the same way. The only thing that would change that is friction, which we're not going to worry about because it's beyond the realm of what you need to do in a high school physics class. Okay, so here's our new tool. We want velocity. Let's try this tool for velocity and see if we have everything we need. So velocity is equal to the square root of 2. Do we know G? We do. It's 9.80 meters per second squared. And then do we know H? We do. It's 7.5 meters. And so we have everything that we need to use that tool. And that tool gives us what we want. So V is equal to the square root. Let's go ahead and multiply this through. We get our units will be meters squared per second squared. And we have 2 times 9.80 times 7.5. Now this 2 came from a formula, right? It came from an algebraic manipulation of 1/2, meaning this is an exact number. This is not going to limit our number of significant figures because it wasn't a measurement. We didn't measure anything. It's just part of our conversion. So which means that we should limit our answer to 2 significant figures. It should be 150 meters squared per second squared. Are we done? Nope, we got to do the square root now. So velocity is equal to, we'll take the square root of this. And it should still be represented in two significant figures. We get our velocity is equal to 12, and then the square root of meter squared is meter. The square root of second squared is seconds. And so our units are meters per second. And why is that nice for units? What are we measuring? Velocity. What are velocity usually presented in? Meters per second. When that happens, as you're doing a problem, it's an indication that you did it correct algebraically. When your units get to a point where it makes sense. Anybody get anything different than 12 meters per second? Okay. So if all of the potential energy converted into kinetic energy, the velocity of your rock would be 12 meters per second. Okay. All right. Now we'll deal with a problem where the object's potential energy does not completely convert. It still has some potential energy. So what is the velocity of the 135.5 kilogram person when they are 250 meters above the ground? So this is going back to the previous example that we did. Mass is equal to 135.5 kilograms. Your initial height was equal to 750 meters. Our final height is equal to what? Well, the final height, if they kept going, would be 0. But this problem gives us the final height for our setup. How high are they above the ground now? 250 meters. So our final height is 250 meters. And then so tools, potential energy is still equal to mgh. We still have this tool that we used last time. Velocity is equal to the square root of 2gh. G is still the same thing, 9.80 meters per second squared. This one's a little bit more interesting though, because we still have some potential energy, right? So we converted some of our potential energy into kinetic, but we didn't convert it all. And this is where what you suggested would actually maybe be, it would take a lot less time than solving our new potential energy, taking that away from the original, and then going and doing the difference. But you could go either way. So you could find our initial potential energy, which we did before. Our initial potential energy was the mass of the human, 135.5 kilograms, times acceleration due to gravity, 9.80 meters per second squared, times our initial height, which is 750.0 meters. And I don't still have that value. What was the value that we got before? $996,000. Thank you. 996,000 joules. So that was our original potential energy. So this is the initial potential energy. Our final potential energy is equal to our potential energy at our final height. The mass of the human is still the same. we assume. They may have been crying in between. That shouldn't impact their mass too much. Any of you ever gone skydiving? How old do you have to be to go skydiving? Do you have to be 18? I know they don't let me because they tell me I weigh too much. It's sad. That's actually true. It's not a joke. I'm not making fun of myself. It is true. So you don't have to laugh. But you can if you want. 250 meters. Man, that's rough. Like I thought I'd get like one chuckle or something. I was telling my class this morning that like 75% of my humor is making fun of myself. And that tends to make people uncomfortable, even when you make fun of yourself. So 75% of my humor makes people uncomfortable, which I'm okay with. I don't know if you are. All right. So how many significant figures are here? It's just 2. That 0 is just for placement, unless we put a decimal place in it, right? Because this could have been, 245. It could have even been like 228, and we were just rounding to the nearest 50. So when we present this answer, we need to present it in 2 significant figures. So the units here will be joules in the same way the other one was. And we have 135.5 times 9.80 times 250. And our new potential energy is 330,000 joules. So according to what we were talking about, we need to subtract this away from our original, and the difference is our kinetic energy. Right? So if we do 996,000 minus 330,000, we get our difference, which is our kinetic energy. Is equal to 666,000 joules. When you subtract or add values, you don't worry about the number of significant figures, you worry about the number of decimal places. So you only worry about the number of significant figures if you are multiplying or dividing or taking the square root. If you're adding and subtracting, you worry about the number of decimal places. This has 0 places after the decimal. This has 0 places after the decimal. This has 0 places after the decimal. Okay? So this is our kinetic energy. Are we done? No, because it's not what we want, right? What do we want? We want velocity. All this to still have to do some more. Can I erase this? So we know that kinetic energy is equal to 1/2 mv squared. And we want velocity, right? So if we change this algebraically, divide each side by 1/2 m. We get that v squared is equal to kinetic energy divided by 1/2 m. But we want velocity and not velocity squared. So finally we get velocity is equal to the square root of kinetic energy divided by 1/2 times the mass. Right? We've used that tool before. We used that not last week. Last week we did a lab, but we used it the week before. Can I erase this? And so velocity is equal to, we can use this tool because we know all of these values. Right? Velocity is equal to the square root. What is our kinetic energy? What's our kinetic energy? 666,000 divided by 1/2 times our mass, 666,000 joules, divided by 1/2 times 135.5 kilograms. And then we get velocity is equal to divided by 135.5. We should present our answer with 3 significant figures. We have 3 significant figures here. We have 4 here. We get that our velocity is equal to 9,830. And then unit-wise, joules are kilograms meters squared per second squared, right? Kilograms will cancel. The square root of meters is what? Or the square root of meters squared? Meters. Square root of seconds squared? Seconds. And so we get a velocity of 9,830 meters per second. Did you get that? So there's our velocity of the human being when they're still 250 meters above the ground. And this again is assuming that there's nothing else involved except for converting potential energy into kinetic energy. So we can do this again using our tool here and just putting in the difference in height, the 750 minus 250 meters. Make sure it gives us the same answer. So does everybody have this written down? Okay. So another tool, we're going to use this tool that says velocity is equal to the square root of 2 times g times the initial h minus our final h. And so we get our velocity is equal to the square root of 2 times 9.80 meters per second squared times 750.0 meters minus 250 meters. All right, so far? Just clean this up a little bit. Velocity is equal to the square root of 2 times 9.80 meters per second squared times 500. And again, when we're subtracting or adding, we don't worry about the number of significant figures, we worry about the number of decimal places. We'll multiply this across. Our units are going to be meters squared per second squared. We get 2 times 9.80 times, we benefited from doing this subtraction in terms of our number of significant figures. Did I ever do, I don't think I ever did the square root over here. Did I?
I was stuck behind because I was trying to figure.
666,000 divided by 135.5. No, I never did. I never did the square root. And so we need to have 3 significant figures, so we have 99.1 meters per second. Not 9,800. That makes more sense. That sounds more reasonable. I left this off, I'm so sorry. But I caught it only because I was given an answer here that was so different.
I was behind because I was trying to do the calculation, I wasn't getting your
This
number.
one. Oh, okay. And so we have 2 times 9.0 times 500. Thank you. Here we have 9,800. And then if we do the square root of that, we get velocity is equal to, and we'll present it as 2 significant figures. Velocity is equal to 99 meters per second. Now when we have more precision, because our number allowed us to have more precision, I'm sorry, that bothered you, didn't it, that it's on the floor? And so this is doing your difference in height in your formula rather than doing the differences in the amount of energy. Either way you do it, we get to the same answer. Our number is a little bit different because of our level of precision that we were able to keep. So doing it that way allowed us to maintain a little bit more precision than doing it this way, but ultimately you get to the same thing. 99 meters per second. Which I forget what terminal velocity is for a human, but it's like maybe double that. There's only a certain point at which you can accelerate based on the shape of our bodies, and then we can't accelerate anymore. Friction overcomes any force of gravity.
Google says it's 53 meters per second.
53 meters per second?
According to Google.
Should be a little bit over 100 miles per hour. I think you could get faster than that. Falcons, peregrine falcons will get up close to 300 miles per hour, but their bodies are a lot more streamlined than us. They're designed to fly. We're not, unfortunately. Okay, so the only thing that you could see in the future, and in the future we may have some problems like this, but we didn't actually work out any today, you don't have any for the homework, is to go in and to see, okay, well, what if we're given the potential energy and you're asked to figure out how high that object is, or what is the mass of that object. So the only thing I wanted to do a little bit before we are done today is just to do some algebraic manipulations of our potential energy equation.
Ronnie Racer for Christmas?
I just have to walk upstairs and grab another eraser. So we have more on site. I just forgot that it wasn't working on this one. All right, so we have this tool that says potential energy is equal to M times G times H. And so if you're given a problem where you're asked to solve for the mass, how would we get mass by itself? Currently we have G and H being multiplied to the mass. So if we wanted mass by itself, we'd divide G and H away. And we'd get that mass is equal to potential energy divided by GH. If you had a problem where it was asking you to solve for the height, how would we get height by itself? Divided by M times G. And we'd get that height is equal to potential energy divided by mass times acceleration due to gravity. You could potentially have a problem where it was asking you to solve for G to verify that G is actually 9.80 meters per second squared, but I probably wouldn't ever do that. Although I did give you a lab where you had to verify G. And your values for G were all over the place, which is fun. You have a low level of precision. The biggest complication is to figure out how much time it actually took. The best way to do that is to record it in slow motion. see where in the video it starts, where in the video it ends. Get a more precise measurement for time. Are there any questions on potential energy versus kinetic? Potential energy, energy associated with position. Kinetic energy, energy associated with velocity. So after seeing it, you coming tomorrow?
Hmm?
You coming tomorrow?
I don't know, maybe.
Maybe.
Yeah.
Okay.
I don't even know.
All right. So